Hello and welcome back to Mech Zone. Previously we were discussing about the numerical methods, and in the numerical methods we have started with the solution of differential equations, and the first method that we were discussing was Euler's method. Okay, and in the Euler's method the general integration the general iterative formula that was used is y of I plus 1 is equals to yi plus h of h into f of xi comma yi. Now here h is the width that we are considering, and f of xi yi is the value of the function at the initial value of x and y. Now we will start our iteration with I is equals to 0, then I is equals to 1, and so on. So we were solving a question where we need to find out the approximate value of y, corresponding to x is equals to 1, and we have been given dy by dx is equals to x plus y, and y at x is equals to 0 is equals to 1. Now for this question what we are doing is we are taking the number of steps as 10 and we are considering the width as 0.1. So what we will do is we will form a table of x plus y is equals to dy by dx, and then y of I plus 1 is equals to y of I plus h into f xi comma yi. Yi or xi is corresponding to the old values of x and y, whereas y of I plus 1 is corresponding to the new value of y. Now we will start our iteration from 0.0. So if x is equals to 0, y has been given as 1, then x plus y simply becomes 1, and y of I plus 1 simply becomes y of I means 1 plus h is 0.1 into value of the function at x0, y0. So at x0, y0 the value of the function is still 1. So we will get 1.01. Now next is 0.1. So when x is equals to 0.1, y we have to keep this value here, that is 1.01, and x plus y would be simply 1.20, and here we will get 1.22. So in the similar manner we are going to complete the table, and we will write 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1.0. Okay, and corresponding to 0.2 value is 1.22, 1.42, 1.36. Then we have 1.36, this value will be copied here, and 1.66, 1.53. Now this value will be copied here, 1.93 and 1.72. Then we have 1.72, 2.22, 1.94. Then 1.94 will be copied here, 2.54, 2.19. Now 2.19 will be copied here again, then 2.89, 2.48. Then in the 8th we have 2.48, 3.89, 2.81, then 2.81, 3.71, 3.18, and in the last we have 3.18. So the required or the approximate value of y at x is equals to 1.0 is coming out to be 3.18. Okay, so this will be the final answer, that is the value of y at x is equals to 1 is approximately equals to 3.18. So this was about the Euler's method. Now we will compare the Euler's method with the modified Euler's method. So now we will have modified Euler's method versus Euler's method. Okay, so in the Euler's method we have y of I plus 1 is equals to y of I plus h into f of xi comma yi. So this was the iterative formula in the Euler's method, and in the modified Euler's method we have the formula y of I plus 1 is equals to y of I plus h into f of x of I plus 1 comma y of I plus 1. So this is the only modification in the formula, which is the modified Euler's formula. Okay, so we actually have to find out y of I plus 1 and x of I plus 1 instead of finding out x of I and y of I. So this was about modified Euler's method. Now we will go for the last method of this chapter, and that is Runge-Kutta method of fourth order. Runge-Kutta method of fourth order. Okay, so in this the general differential equation will be given in the form dy by dx is a function of x and y at x0 is equals to y0. This will be the general given information. Okay, so what we will do, we will find out four constants. They are k1, and k1 is h f of x0 comma y0. So k1 is equals to h of x0 comma y0. k2 is h of x0 plus half h and y0 plus half k1. Then we have k3. k3 is h of x h into f of x0 plus half h y0 plus half of k2, and we have k4, that is h into f of x0 plus h y0 plus k3. So in the two middle constants, that is k2 and k3, we observe that half has been used here and half has been used here, whereas in the first and the last we have no half. That means simply we have x0 plus h1, sorry, this is not h1, this is h. Okay, and then we will find out final k is equals to 1 upon 6 k1 plus 2 k2 plus 2 k3 plus k4. Okay, so this is quite a lengthy method, but we have to follow it as given. So what we are doing is we are finding out the values of k1, k2, k3 and k4, and finally the value of k. So let us do one question in which we have been given, by applying the Runge-Kutta fourth order method, we have to find out the approximate value of y. Find approximate value of y when x is equals to 0.2, and we have been given that dy by dx is equals to x plus y, and y at x is equals to 0, this is equals to 1. Now let us solve this question, and we have been given that initially x0 has been given as 0, y0 has been given as 1, h is equals to, let us take h is equals to 0.2. Okay, so h हो गया हमारा 0.2, and f of x0 comma y0 कितना हो गया, ये हो गया 0 plus 1, it becomes 1. So k1 would be h into f of x0 comma y0. This would be 0.2 into 1, this is 0.2. Now the value of k2, it would be h into f x0 plus 1 by 2h y0 plus k1 by 2. So this would be 0.2 into f of 0.1 comma 0.1, once again, sorry, 1.1 So this is coming out to be 0.2400. Now the value of k3, h into f, x0 plus h by 2, y0 plus k2 by 2. So after solving, the value is coming out to be 0.2440. Now the value of k4, it is hf, x0 plus h, y0 plus k3, and this is coming out to be 0.2888. And the value of k is 1 by 6 k1 plus 2k2 plus 2k3 plus k4, and this is coming out to be approximately 0.2428, and y1 is equals to y0 plus k. So y1 simply becomes y0 was 1 plus 0.2428, so it is coming out to be 1.2428. So the approximate value of y which is being required is coming out to be 1.2428. So with this we come to the end of this chapter, and I hope that you have really understood well. So please give us your valuable feedbacks on our channel, or you can also give us your feedbacks on our Facebook page. You can rate our Facebook page. We have our Facebook page by the name of Mech Zone, and also subscribe to our channel and press the bell icon so that जितने भी updates होते हैं आपके पास वो सबसे पहले पहुंच सके. So now we will start with the next chapter, and that is the complex variables. So now we will start with the new chapter, that is complex functions. Now we already know what are complex numbers, and we have already studied these numbers when we were there in our class 11th and 12th. So complex number are generally in the form of a plus ib, where a and b are real numbers and I is called as the iota, that is under root of -1. So there is some real part and there is some imaginary part. So these numbers are called as complex numbers, that is numbers which are having both real as well as imaginary part. Okay, so the first thing that we will start in this chapter is the complex functions. Okay, and in the complex functions, then let us define a variable z such that z is equals to x plus iy. Okay, and this is having this is the complex variable in a given region R, where R is representing the real numbers, and in this region we have one or more values of w such that w is equals to u plus iv, where u is a function of xy and v is also a function of xy. Okay, where u is actually a function of z, and where w is actually a function of z and u and v are the functions of x and y. So we can simply write w is equals to u xy plus I times v xy. This is nothing but it is a function of z. Okay, then to each value of z there corresponds one and only one value of w. Then w is said to be a single valued function, otherwise it will be called as a multi-valued function. Okay, so let us give one example. For example, w is equals to 1 by z is a single valued function, whereas w is equals to under root z is a multi-valued function of z. Okay, this is defined at all the points except at z is equals to 0, because 1 upon 0 that will give us infinity, whereas this is actually having, okay, so this is actually having two values, because under root 4 can be written as plus minus 2. For example, agar hota x square is equals to 4, then we get x is equals to under root 4, that is plus minus 4, and this will be plus minus 2. So we are getting two values, hence it is a multi-valued function, except for z is equals to 0. Okay, so this is a single valued function and this is a multi-valued function. Now we will discuss about the exponential functions of a complex variable. Okay, so here we will just have a recap of the exponential functions that we have already studied in our 11th and 12th. That is, e to the power x is equals to 1 plus x upon 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus so on. Okay, so we can also define this exponential function of the complex variable such that z is equals to x plus iy. So e to the power z can be written as 1 plus z upon 1 plus z square upon 2 factorial plus z cube upon 3 factorial plus so on. Okay, now we know that z is equals to x plus iy, and if we put x is equals to 0, then z is equals to iy, and e to the power z, that is e to the power x plus iy, would simply be e to the power iy, and e to the power iy can be written as 1 plus iy upon 1 factorial plus iy whole square upon 2 factorial plus iy whole cube upon 3 factorial and so on. And we know that I square is equals to minus 1 and I cube, I is equals to under root of minus 1, I cube is equals to then we can also evaluate I cube also. Okay, I cube is I square into I, and this would be minus I. Okay, so this can be written as 1 minus y square upon 2 factorial plus 5 to the power 4 upon 4 factorial so on plus I into y minus y cube upon 3 factorial plus y to the power 5 upon 5 factorial and so on. So this can be actually deducted, and this is actually a series of cos y and plus I, and this is a series of sine y. So e to the power z, which is e to the power x dot e to the power iy, matlab e की power x plus iy can also be written as e to the power x dot e to the power iy, and hence this can be written as e to the power x cos y plus I sin y. ठीक है, हमने x को 0 ले लिया था तो 0 लेंगे तो ये 1 हो जाएगा, तो वो सिंपली ऐसा आ गया. तो x plus iy is nothing but r cos theta plus I sin theta, and in general it can be written as r e to the power I theta. So exponential form of z is equals to x plus iy can be written as r e to the power I theta. Okay, so this is the general exponential form of the complex variable. Now we will discuss about the circular function of a complex variable. Circular function of a complex variable. Okay, now from the above discussion we can write e to the power iy is equals to cos y plus I sin y, and e to the power minus iy can be written as cos y minus I sin y. So the circular function can be written as sin y can be simply written as e to the power iy minus e to the power minus iy upon 2i, and cos y can be written as e to the power iy plus e to the power minus iy upon 2. Okay, so it is therefore natural to define the circular functions of the complex variable z by the equations, that is sin z is simply equals to e to the power iz minus e to the power minus iz upon 2i, and consecutively cos z can be written as e to the power iz plus e to the power minus iz upon 2, and tan z can be simply evaluated as sin z upon cos z. So by using the Euler's theorem, cos z plus I sin z can be simply written as e to the power iz plus e to the power minus iz upon 2 plus I times e to the power iz minus e to the power minus iz upon 2 I. Okay, so this can be simply written or it can be solved as e to the power I z, क्योंकि I cancel हो जाएगा and it will come out to be e to the power I z, where e to the power I z, where z is equals to x plus I y, and e to the power I y is simply cos y plus I sin y. Okay, we have to remember this result. The second theorem is the de Moivre's theorem. De Moivre's theorem, and de Moivre's theorem states that cos theta plus I sin theta whole to the power of n is equals to cos n theta plus I sin n theta, or this can be simply written as e to the power I n theta. Okay, so cos theta plus I sin theta whole to the power of n is equals to cos n theta plus I sin n theta, or simply e to the power I n theta. And this is true, this theorem holds good for both real and complex numbers. It holds good both for real and complex numbers. Now we will have some hyperbolic functions, and hyperbolic function, say sine hx, this is equals to e to the power x minus e to the power minus x upon 2, and cos hx is e to the power x plus e to the power minus x upon 2. So this is called as the hyperbolic cosine function, and this is known as the hyperbolic sine function of x. So here we can notice that in the denominator we are not having the term of I. Okay, now I will write down some important conversions between the hyperbolic and the normal angle formulas, that is sine Ix is equals to I sin hx, cos Ix is equals to cos hx, cos वाले में I नहीं आएगा. Then we have tan Ix is equals to I tan hx. Then sin hix can be written as I sin x. Then cos hix is cos x, and tan hix is I tan x. So this is an important table and we have to remember this table. Okay, so we have to remember those formulas. Now we will start with the logarithmic function of a complex variable. Logarithmic function of a complex variable. So we have already defined that z is equals to x plus iy and w is equals to u plus iv, where this is actually a function of z and u is a function of x and y and v is also a function of x and y. Okay, so now what we will do is then we will define then w is said to be a logarithm of z to the base e, and w is written as log z to the base e. इसको हम ऐसे भी लिख सकते हैं. So e of w plus 2i n pi can be written as e to the power of w dot e to the power of 2 pi I n. This is simply equals to z. So log of z can be written as w plus 2 pi I n. And why? Because since e to the power 2 pi I n is equals to 1. आप 2 pi रख के इसमें देखिए it is coming out to be 1. Okay, now what we will do is, first is if y is equals to 0, then log x is equals to 2 pi I n plus log x. Okay, and this is actually telling us that logarithm of a real quantity is also coming out to be a multi-valued function. Okay, and this is an important discussion. And if we wish to write down the logarithm of a negative quantity, then it can also be written as log 2 into minus 1. So this can be log 2 plus log e to the base of minus 1. Then this is log 2 plus I pi. So this is coming out to be log 2 to the base is simply 0.6931 plus I times 3.1416. Okay, so this is how we can write down the logarithm of the negative values. And since minus 1 can be written as cos of pi plus I sine of pi, or simply e to the power I pi. Theta की जगह pi रख दिया तो we will get minus 1 here. Okay, now let us evaluate the real and imaginary parts of the logarithmic of x plus I y. Now we know that log of x plus I y is simply equals to 2 pi I n plus log of x plus I y. ठीक है, क्योंकि हमारा ये जो पार्ट हो गया, ये तो पार्ट हमारा क्या हो जाएगा, 0 हो जाएगा, और ये हो जाएगा हमारा तो 0 प्लस, इसको ऐसे भी लिख सकते हैं. सो नाउ व्हाट विल डू इज 2 pi I n plus log of x plus I y can be written as r cos theta plus I sin theta, and we will solve it and we will get 2 pi I n plus log of r plus I theta. So this would be log r is equals to under root of x square plus y square plus I theta plus 2 pi I n. So this actually becomes the real part, and if we take I as common, then it would be I theta plus 2 pi n. This becomes the imaginary part, and theta is nothing but it is called as the argument of the complex number, and theta is nothing but tan inverse y upon x. So log of under root x square plus y square is the real part, and theta plus 2 pi n is the imaginary part. Okay, now we will start with the Cauchy-Riemann Theorem. Okay, and this theorem is very important in the complex number, and according to this theorem, the necessary and the sufficient condition for the derivative of the function, that is w is equals to u plus iv, where u is a function of xy and v is also a function of xy, to exist for all values of z in a given region R, then del u upon del x, del v upon del x, del u upon del y, del v upon del y are continuous functions of x and y in this given region R. So these are all continuous functions of x and y in the region R. Okay, this was the first condition. Second condition was del u upon del x is equals to del v upon del y, and del u upon del y is equals to minus del v upon del x. So this relation is actually called as the CR equations, or the Cauchy-Riemann equations, and Cauchy-Riemann equations has to be satisfied to find whether a given function is a continuous or not in that given span of region R. Okay, so if z is equals to x plus iy, then the derivative, that is f dash z, can be written as del u upon del x, because f of z is actually u plus iv, that is w. So del u upon del x plus I del v upon del x, and this can also be written as del v upon del y minus I into del u upon del y, because del u upon del x is equals to del v upon del y, and del v upon del x is equals to minus of del u upon del y. So this was all about the Cauchy-Riemann equations. Now what we will do, one question, we have been given w is equals to log of z, and we have to find whether it is analytic or a non-analytic function. So if we have to find out whether a given function is analytic or not, then if it is analytic, then it will definitely satisfy these CR equations. So w has been given as log z. So w is equals to log of u plus I v, and we have already derived that log of u plus iv, w is equals to u plus iv. Okay, this is equals to log of x plus iy. Now log of x plus iy can be written as log of half log x square plus y square. This is nothing but log of under root x square plus y square plus I tan inverse y by x. Now this is the real part, that is u, and this is the imaginary part, that is, along with the imaginary part we have v. So u is equals to half log x square plus y square, and v is equals to tan inverse y by x. Now we will find del u upon del x, and this is coming out to be x upon x square plus y square, and this is nothing but it should be equals to del v upon del y. Okay, and del u upon del y is equals to y upon x square plus y square, simple partial differential, and this should be equals to minus del v upon del x. Okay, so ये वही चीज है, अगर हमारा v ये दिया हुआ है, tan इनवर्स y by x को भी हमने डिफरेंशिएट करेंगे तो यही रिजल्ट्स आएगा. तो यहां से तो हमारी Cauchy-Riemann इक्वेशन सेटिस्फाई हो रही है, हेंस द फंक्शन इज एक्चुअली एनालिटिक. ठीक है, अब एनालिटिक भी हमें चेक करना पड़ेगा, हर पॉइंट पर एनालिटिक है या कहीं पर एनालिटिक नहीं भी है. ठीक है, सो व्हाट वी विल डू इज वी विल फाइंड dw अपॉन dz, दिस इज नथिंग, del u अपॉन del x प्लस I del v अपॉन del x. तो जब हम इसको सॉल्व करेंगे ये वैल्यूज यहाँ पे रख के, तो वी विल फाइंड इट इज इक्वल्स टू 1 अपॉन z, एंड फॉर 1 अपॉन z द z शुड नॉट बी इक्वल्स टू 0 बिकॉज वहां पे वो नॉट डिफाइंड हो जाएगा. सो द अबव फंक्शन, दैट इज w इज इक्वल्स टू log of z, इज एनालिटिक एवरीवेयर एक्सेप्ट z इज इक्वल्स टू 0. Now we will do a question which has been asked, and this question is an important one, and we have been given an analytic function. An analytic function has been given for a complex variable z is equals to x plus iy, such that f of z is equals to u xy plus iv xy, where I is equals to under root of minus 1. If u is equals to xy, then what is the expression for v? What would be the value for v? Now since this has been given analytic, it means it will follow or it will satisfy the Cauchy-Riemann equations. So we have been given that it is a analytic function, so del u upon del x is equals to del v upon del y, and del v upon del x is equals to minus del u upon del y. So these equations needs to be satisfied if this function has to be an analytic one. So what we will do is we have ux that is simply del u upon del x. This is equals to vy, and vx is equals to minus uy. This is nothing but these equations have been written in this form. Okay, now we know that vy is equals to y and vx is equals to minus x, because x has been given, del u upon del x is y, so this is, and del v upon del x is equals to minus del u upon del y, so here we'll get minus x. Now what we'll do is vy simply means del v upon del y, this is equals to y. Now we will integrate both the sides, and on integrating we get y is equals to v is equals to y square upon 2 plus some constant c. And what we will do is we will differentiate this v with respect to x on both the sides. So we or simply we can say vx is actually if we will differentiate this with respect to x, we will get 0, plus if we will differentiate this with respect to x, we will obtain some function of x such that we will write it as f dash x. And since vx has been given as minus x, so we can write f dash x is equals to minus x. So df upon dx is equals to, or we can simply write c dash x because we have used c. So dc upon dx is equals to minus x. So dc would be integration of minus x dx. So this would be minus x square upon 2 plus some other constant c2. Okay, so from here we obtained that y is equals to, or if we keep the value of c here, then we will obtain y square upon 2 minus x square upon 2 plus k. Okay, so we can simply write it as y square upon 2 y square minus x square upon 2 plus some constant k. So this is the best suited answer. So this numerical is important because here we are actually evaluating one of the variables if u or v have been given. अगर यहाँ पर हमें v दिया होता, u नहीं दिया होता, तो भी हम same procedure follow करके अपना आंसर निकाल सकते थे. Now we will do one more important question, and we have been asked that what are the square roots of minus I? What are the square roots of minus I? Now minus I can be simply written in the form of a complex number, that is cos of minus pi by 2 plus I sine minus pi by 2, because cos 90 is 0 and sine of minus 90 is minus sine 90, and this would simply be minus 1. Now since we have to find out the square root, or this can also be written as cos of 3 pi by 2 plus I sine 3 pi by 2. Now for the square root, that is, this is simply minus I, and we have to take the square root, so we will write minus I to the power of 1 by 2 will be equals to cos of minus pi by 2 plus I sine minus pi by 2 whole raised to the power of half. So this is cos theta plus I sine theta whole to the power of n, and this would simply become, so by applying the De Moivre's theorem we will get cos of minus pi by 4 plus I sine minus pi by 4, and this is nothing but cos of 3 pi by 4 plus I sine 3 pi by 4. So this becomes the answer, and we have obtained it by applying De Moivre's theorem. Okay, now we will start with the line integral of complex variable. Line integral of complex variable. And in the line integral of complex variable, the first method that we will discuss is for the indefinite integration and substitution. Okay, and in this method we are simply substituting the limits. For example, a to b f of x dx, this is simply equals to f of b minus f of a, that is the function value at the upper limit minus the function value at the lower limit. And there is a theorem that is from z0 to z1 f of z dz, this would also be equals to f of z1 minus f of z0. So there is nothing, we simply have to remember this case, and I will solve one question. For example, integral 0 1 plus I z square dz. Now we know that the integral of z square is z cube upon 3, and we will keep the limit from 0 to 1 plus I. So this can be simply written as 1 upon 3 z cube, and this is 1 upon 3 1 plus I whole cube. So this is nothing but if we will solve, we will get 2 upon 3 plus 2 upon 3 I. Okay, so this would be the answer for the line integral of this complex variable z. So that was the first method. Now we will move on to the second method, and it is called as the path integral. This is called as the path integral. So path integral simply means we are integrating with respect to path. For example, we have been given this question, this is one path and this is the other path, such that this is C1 and this is C2. Origin, this is 0, 0. Say this is 0, 2, and here we have the coordinate 4, 2. So the total integral would be integral along the curve C1 plus integral along the curve C2 will give us the answer. Or in general we can remember C u dx minus v dy plus I times integral u dy plus v dx along the curve C. So where z was x plus iy, so dz would be simply dx plus I dy. Okay, तो यहाँ ये हो गया हमारा path integral वाला formula. And there is one special case that we have to remember. Closed integral around a circular path in the counterclockwise direction. So closed integral of dz upon z about a circular periphery or about a circle, a unit circle, that means it is having a radius of 1. This is equals to 2 pi I. So this is a very standard result and it needs to be memorized because direct question भी इस बार हो सकता है आ जाए. ठीक है, तो ये आपको याद रखना है. Closed integral of dz upon z around about a circle C, it is equals to 2 pi I. And another important case, that is closed integral of z minus z naught to the power m dz. This is equals to 2 pi I for m not equals to minus 1, and this is equals to 0 if m is equals to for m equals to minus 1, and this is m not equals to minus 1 and integer. So this can be written as closed integral of 1 upon z minus z naught dz. This is equals to 2 pi I. So this is also the important result and we have to remember this. Okay, so this was all about the line integral and related things, and now we will start with the most important part, that is the Cauchy's theorem. Cauchy's theorem. In the Cauchy's theorem we have to remember just one thing: closed integral f z dz, this is equals to c u dx minus v dy plus I times integral v dx plus u dy. So where f of z is an analytic function and f dash z is continuous at each point within and on the closed curve C. ठीक है? Then closed integrals, then this fz dz is equals to 0. And if f of z is equals to u plus iv and dz is nothing but dx plus I dy, then the integral this can be written. So integral f of z dz is equals to 0 if f of z is an analytic function and f dash z is continuous at each point within and on the closed curve C. ठीक है? तो ये तो था हमारा Cauchy's theorem and this is a very important theorem. Okay. Now we have the Cauchy's integral formula. We have the Cauchy's integral formula, and the Cauchy's integral formula states that if f of z is analytic within and on the closed curve, and if a is any point within that closed curve, within the closed curve C, then f of a is equals to 1 upon 2 pi I integral f of z dz upon z minus a. Okay, where what is a? A is any point which is within the closed curve C. Okay, and the function is analytic at all the points within C except it is analytic at z is equals to a. Z is equals to a पर हमारा फंक्शन एनालिटिक नहीं होगा, रेस्ट सारे पॉइंट्स पर हमारा फंक्शन एनालिटिक हो जाएगा. तो अगर f of a की वैल्यू हमने तो आप निकाल दी, अगर f dash a निकालना हो तो दिस इज नथिंग बट 1 factorial upon 2 pi I. Okay, then we have, or in general if I need to write down, f की power na, this is equals to n factorial upon 2 pi I integral f of z upon z minus a to the power of n plus 1 dz. So we have to remember this case, and this is the Cauchy's integral formula. This point is simply telling you that the function is not analytic at this point and rest at every point it is analytic. Now let us do one question and I will explain you how to use this formula. And in this question we have to use the Cauchy's integral theorem and we have to find out the value of z cube minus 6 upon 3z minus I such that it is closed integral around a closed curve C, and this has been taken the counterclockwise direction. Now if we compare it to the standard Cauchy integral formula, we know that f of a is equals to integral 1 upon 2 pi I integral f of z upon z minus a dz. So we are actually comparing. So अगर इसको हम कंपेयर करें तो यहां से f of z upon z minus a closed integral, this is dz, this is equals to 2 pi I into f of a. Now we have z minus a and we are here having 3z minus I. So if we take 3 common from here, we will obtain z cube minus 6 upon 3 z minus I by 3. So we can write 1 upon 3 z cube minus 6 upon z minus I by 3. So here we get z minus a. So a is actually I by 3. Okay, now a is coming to be I by 3. F of z, if we compare, we are getting as z cube minus 6. So 1 upon 3 into this value simply means 1 upon 3 into f of a. Okay, so that is 1 by 3 into what is the value of z, a हम लोग यहाँ पर a रख देंगे, that is I upon 3 whole cube minus 6 and multiplied by 2 pi I. So we will obtain the value as 2 pi upon 81 minus 4 pi I. तो वही कॉशी इंटीग्रल फॉर्मूले से हमने कंपेयर किया, a की वैल्यू इवैल्यूएट करी और इस फंक्शन की वैल्यू हमने z इज इक्वल टू a पर इवैल्यूएट कर ली. So this is the final answer. Now we will discuss about what is the meaning of zero of an analytic function. So the zero of an analytic function is that value of z for which f of z is equals to 0. Okay, then that is called as zero of the analytic function. Now we will discuss about the various singularities of analytic function. Singularities of the analytic function. So now we will discuss about the different types of singularities, and first is the isolated singularity. So in case of the isolated singularity, we have z is equals to a is called as the isolated singularity of f of z such that this function is analytic at each point in the neighborhood. Then z is equals to a is called as the isolated singularity, that is there exists a circle with center at which there has no, मतलब इसके अलावा और कोई भी singularity ना हो, then that is called as the isolated singularity. Okay, and what do we mean by singularity or a singular point? So singularity was singly or a singular point may be defined as a point at which the function ceases to be analytic. मतलब जो हमारा singular point है उस point पे हमारा function analytic नहीं होगा, और अगर सिर्फ एक ही ऐसा point है जहां पर हमारा function analytic नहीं है, then it is called as the isolated singularity. Next we have the removable singularity. Okay, the removable singularity में क्या होता है? If all the negative powers of z minus a in the expansion series of n is equals to 0 to infinity an z minus a to the power n, ठीक है, can be removed in such a way that it becomes the analytic at z is equals to a. मत पेन खत्म हो गई. तो अगर इसके एक्सपेंशन में से नेगेटिव पावर्स जो हैं उसमें से हमारा z is equal to a पर सिंगुलैरिटीज हमारी रिमूव हो रही हैं, then such type of singularity is called as removable singularity. And what are poles? Poles जैसे मान लीजिए if all the negative powers of z minus a in this expansion after the, then the singularity is called as z is equals to a, and this is simply called as pole of order n. ये कहलाएगा हमारा pole of order n. ठीक है. Next we have the essential singularity, and the essential singularity, if the number of negative powers of z minus a is infinite, then z is equals to a is called as the essential singularity such that limit z tends to a f of z it will not exist. ये exist ही नहीं करेगा. ठीक है. So there is a difference between pole, singular point and zero. इन तीनों points में आपके differences है. So we should definitely remember that there is a difference between pole, singular point and zero. These three terms are actually different from each other. Now let us do some questions where we need to determine the singularities. Say this function f of z has been given as z minus 1 upon z square plus 1. And we have to find out the singularities. Now singularity is a point at which the function ceases to be analytic. And if this is equals to 0, that is z square plus 1 equals to 0, then we have z square is equals to minus 1, then z is equals to plus minus I. So z is equals to plus minus I simply becomes the singularities. So this is a very, very simple numerical. Now we come to another important topic, that is residue. And residue is nothing but it is let me tell you, an is equals to 1 upon 2 pi I f of z upon z minus a to the power n plus 1 dz. Only this formula we have to remember. And what is the residue theorem? In the residue theorem, we have integral f of z dz. This is equals to 2 pi I into the sum of residues at the singular points within C. मतलब जो within C के within जो points होंगे सिर्फ उसी points पर हमें अपना residue calculate करना है, and we will multiply it by 2 pi I, so we will get the value of integral f of z dz. Okay, now we will go for the calculation of residues. Now for the calculation of residues, we have residue of a function f of a is equals to limit z tends to a z minus a into f of z. So this is the first method. The second method is residue of f of a is equals to phi of a upon psi dash a, where psi dash is nothing but it's the differential of the function psi. Now if the pole is of order n, for example pole of order n, then the residue can be calculated as 1 upon n minus 1 factorial d की power n minus 1 dz n minus 1 z minus a to the power n f of z, and all this has to be evaluated at z is equals to 0. Okay, and this formula is very important because it is determining the residue corresponding to a pole of the order n. Okay, so for example if we get z square is equals to 4, so z is equals to plus minus 2. Now let us solve a very important question, and we have to find out the integral f of z dz evaluated around the unit circle. Unit circle simply means mod of z is equals to 1. It is having a radius of 1 unit, such that f of z has been given as cos z upon z. Okay, now we will first find out the pole, and we will also find out whether it is a simple pole or it is a pole of order n. So if we equate z is denominator equals to 0, we find that the pole is only 0. So now we will find the residue, and residue would be residue of f of a, this is equals to limit z tends to a z minus a into f of z. So this would be limit z tends to 0 z minus 0 into f of z is given as cos z upon z. So z gets cancelled out, and here we will obtain 1. Okay, so what would be the residue, or sorry, what would be the integral? Integral is equals to 2 pi I into the residue within the closed curve, because z is equal to 0 definitely will be involved, or it will be included within the curve, closed curve, or the circle which is having a radius of 1 unit. So 2 pi y into 1, that is equals to 2 pi I. So this is the answer. Now we will do another important question, such that this has been given as mod of z minus I is equals to 2 1 upon z square plus 4 dz in the positive sense. So we have to find out the value of this integral. Now we know that the poles can be found out by simply z square is equals to 4. Z square is equals to minus 4. So z is equals to plus minus 2i. So z is equals to 2i and minus 2i. So we know that these points 2i will be lying here and minus 2i will be lying here. Okay, and we have been given mod of z minus I is equals to 2. So mod of z minus I is equals to 2 simply means that x plus iy minus I mod is equals to 2. So x plus I y minus 1 is equals to 2. This means that the circle is having a center at 0, 1. दोनों को इक्वेट कर देंगे तो ये हो जाएगा circle is having a center at 0, 1. So this point is actually 0, 1. And it is having a radius of 2 units. Now since it is having a radius of 2 units, so 1 plus 2 would be 3i, and in the downward direction 1 minus 2, that is minus 1. So we will get only I. So circle would be somehow like this. So we find that minus 2i point is not included in the circle, however 2i point is included. So z minus 2i is the pole that we have to include. Okay, so now we have to find out the value, that is 2 pi I into the residue at points within the closed curve. Okay, so we have to find out the residue at this point, that is 2i. So अगर यहाँ पर हम लोग क्या रख दें, 2i रख दें, तो हो जाएगा 2 pi I into the 2 pi I into the residue of f at 2i. So इसको हम लोग क्या लिख सकते हैं, we can write this as 1 upon z plus 2i z minus 2i. Limit z tends to 2i z minus 2i, मल्टीप्लाई कर देंगे तो ये कट गया, तो हो जाएगा 1 upon z plus 2i. तो instead of z we will keep 2i, so 1 upon 2i plus 2i, this simply becomes 1 upon 4i, 1 upon 4i, and we have to multiply it by 2 pi I. ये ना भूलें क्योंकि अगर आप ये भूल गए तो सवाल गलत हो जाएगा. So 2 pi I into 1 upon 4i, we will obtain pi by 2. So the correct answer is pi by 2. So we have to keep in mind whether these points are actually lying inside or whether they are lying outside. We have to only calculate the residue at those points which are lying inside. So with this we come to the end of this chapter on complex numbers. However, we are still left with one more chapter, and that is calculus. And in calculus I will not be teaching about the differentiation and the integration. Rather I would be focusing more on the functions, continuity and discontinuity limits, and L'Hopital's rule, and then Euler's theorem also. And in the chapter of Laplace theorem, I will be simply discussing the formulas, and only the formulas would be more than enough for you to score well in that particular chapter of Laplace transform, because Laplace transform is not included in mechanical to a greater extent, but some questions may be asked directly formula based, but it is very highly used in electrical engineering and electronics engineering. So thank you so much for today. Do subscribe to our channel and also give us your positive feedback. You can download the entire study material absolutely for free from the description link in the given below, description link which has been given below in the video. And I hope that you will give us very good feedbacks. So with this, thank you so much for today.